So we had just gotten to selective precipitation. I mean, we can predict things by Q and K, whether or not they're going to precipitate, but selective precipitation is where you add a reagent that precipitates one thing but not another or others, as will be the case with qualitative analysis. First, though, we're going to talk about quantitative precipitation. Or really, I guess the quantities involved in precipitation. So you can do selective precipitation if you've got K values, KSPs, where the factor, again, at least 10 to the 3, that pops up a lot. As you're hopefully now noticing. So if we had a solution that contains barium, lead, and calcium ions, lead-2, and we add sulfate to the solution, which cation precipitates first? So one of the first things to consider is, as we talked about before, KSPs are not always directly comparable, because if something produces a different number of ions, so if I was comparing like, well, I don't know, aluminum to calcium, and I was looking at chlorides, which I know is not a thing, but 3 ions versus 2 ions means that they'll have different solubilities in solution. And so that could flip the KSP. What we actually need is molar solubility, where you take the KSP and you calculate what is the molarity of, or I guess the base molarity of ions that'll be produced. We already don't have to think about that for this problem though, because everything's 2+, and we are reacting them all with sulfate, so they will all have sort of a 1-to-1 ratio between cation and anion. So after making sure that that's the case, then we can go through here and we can find calcium sulfate, barium sulfate, and lead-2 sulfate, not sulfide. And again, because it's all cation plus sulfate, just one sulfate, we can compare these KSPs directly. So which of these will precipitate first? Good, going for something on one of the ends. KSP means it's the least, or small KSP means it's the least soluble. So barium sulfate's the least soluble. So when I add sulfate to it, it'll precipitate first, because it takes the smallest amount of sulfate to precipitate. So barium sulfate's 10 to the minus 10, which is smaller than 10 to the minus 8, which is smaller than 10 to the minus 5. So you'd see barium sulfate precipitate first because it's the least soluble.
Small KSP means it will favor the precipitant.
Yes. Yes. Yeah, because the small KSP means it'll favor the precipitate, because if I write out BaSO4, I mean, honestly, on any question that is the most, go for one of the ends. Don't go for something in the middle. Most or least, it's going to be on an end. Which I hate absolutes, so my brain's immediately like, there's got to be a situation where that's not the case. It probably is. Yeah, so because the reaction that we're talking about here for the precipitation or dissolution of barium sulfate, it's written with barium sulfate as a reactant. That means a small KSP favors the reactants, which means that for any amount of sulfate in here, or sorry, for any amount of barium in here, it only takes a small amount of sulfate, or at least a smaller amount of sulfate than it would for calcium. Now, if we are precipitating one of these first, again, going back up here, if the difference, or we need a difference in K values, KSP, of at least 10 to the 3, then I could use selective precipitation for barium, and I could separate out barium from calcium sulfate, because I could precipitate the barium first. Once that's done precipitating, basically none of the calcium is going to precipitate. Lead sulfate, on the other hand, I could precipitate out the barium, but I would also be losing some of the sulfate because they're not far enough apart. There'd be some overlap. Might not be significant, but the 10 to the 3 is a rule of thumb anyway. So let's take a look at doing actual calculations with this. So magnesium and calcium are present in a solution. We're given molarities. And they can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide concentration triggers the precipitation of the magnesium 2+ ion? It says they can be separated by selective precipitation, and if we look at their KSPs, 10 to the minus 13, 10 to the minus 6, yeah, those are like 10 to the minus 7 apart, or 10 to the 7 apart. And then really it's extra information that we're given the calcium concentrations here. Because really what we're concerned with in figuring out when the magnesium precipitates is taking the magnesium hydroxide, and we're looking at this reaction at 2 OH minus. And so we're not really doing an ice table here, we're doing more of an equilibrium expression. So the equilibrium expression for this, because magnesium hydroxide is a solid, we're not even going to worry. Actually, I'm not going to put 3 because that looks like an ice table. Really what we're doing is KSP equals the concentration of Mg2 plus, concentration of hydroxide squared. You don't really need to write it in, but it's over 1 because our reactant is a solid. So products over reactants raised to the power of their coefficient. And we have KSP. Right, and so KSP is that tipping point, where if I have any more magnesium concentration or hydroxide concentration than is equal to, according to this equation, KSP, then things will precipitate. So the minimum amount of hydroxide required would be right at this tipping point. Any more than that would cause precipitation. And so I want to know, what would the concentration of hydroxide be at equilibrium? So this is OH minus squared. All right, so this is going back like way back, chapter 16. We first talked about equilibrium, and it's like you can plug 2 things in, or if you can plug in every number except for 1, then you can solve for it. So 2.06 e to the negative 13 divided by 0.025, and that raised to the 1/2. So 2.87 times 10 to the negative 6 molar equals my hydroxide concentration. And if we wanted to know the concentration of hydroxide required to precipitate the calcium, we do essentially the same thing, but plug in the KSP for calcium hydroxide and the concentration of calcium, sulfur hydroxide. And it ends up being something times 10 to the negative 2. Much bigger than this. All right. It's really annoying. I'm like trying to click the orange thing. Can't click the orange thing if you're not on the right tool. The washi tape. Okay, so that's if we're looking for, right, the concentration where one thing precipitates. This is a more complicated problem, but it's actually not that much more complicated. So solution is 0.085 molar in lead 2+, 0.025 molar in silver. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? That sentence could be rewritten. So something's going to precipitate first. How much sodium chloride is required to precipitate that thing? And this is actually an example of a problem where now we have PbCl2 and AgCl. Right, so I've got lead 2 chloride, which has 2 chlorides, and I have silver chloride, which has 1 chloride, which means that I cannot just directly compare the KSPs to figure out which one's going to be less soluble. I would have to calculate molar solubility. But we kind of need to calculate the concentration of sodium chloride anyway. So we could do molar solubility, figure out which one's less soluble, and then just calculate for that one. But I think that's actually one more step than just calculating the concentration of sodium chloride needed to precipitate each. So this is the same thing that we did in the previous slide. Again, always start out by writing out the equation. It's going to be 2Cl minus. And again, not nice table. We're just using KSP. So my KSP for lead is 1.17 times 10 to the negative 5. And that's equal to the concentration of lead, which I was given. Times whatever chloride concentration it's going to take. So chloride concentration squared. And I need you to say in your head, this is not nice table. Because the temptation will be that when you write all this stuff out, especially if you write out the equation and you start writing concentrations under it, we've done so many ice tables that your default is going to be to start writing in like X and 2X. And then if you put 2X in here for chloride, you're going to get the wrong number. Because that's an ice table. That's when things are shifting. If I'm producing solids from lead 2 chloride, I'm going to get twice as many chloride ions. But that's not what we're talking about here. I'm just saying the concentration of the chloride in the solution. So I don't need to double it. It's just the chloride concentration. Shouldn't have put my calculator away. I really missed slide over. Can you? The newest update, they added this, which is cool. But like, why'd they have to kill my boy? Look what they've done to my boy. Sorry. So, calculating. Zero 0.0117 molar equals concentration of Cl minus required to precipitate my lead 2 plus. And now we rinse and repeat for silver chloride. That's aluminum. And again, not a nice table. And this concentration was 0.025. And that's just going to be Cl minus, not squared. I typed that in really weird. Oh, I hit the wrong button. That's what it was. I think this is one of those numbers that if you have a TI-36X Pro and maybe other calculators, it'll just say 7. Like it'll be a whole bunch of zeros and then 7. You can, if you have a TI-36X Pro, if you hit mode and then you go down to, mode, and then on the second line, there's norm, psi, and ENG, SCI and ENG. Psi will turn everything into scientific notation, which is a little bit annoying because then if it's even like times 10 to the minus 1, 0.1 becomes scientific notation. But this does have at least a couple more decimals. So this is the concentration required to precipitate silver chloride. So which one precipitates first? Yeah, silver chloride. One way to think about it is that if you're starting at 0 chloride ions, as you add chloride ions, whichever one of these you hit first is going to precipitate first, because that's the smaller amount of chloride ions. So it takes 10 times 10 to the minus 9 molar chloride to precipitate silver chloride, so that's definitely going to precipitate first. So then we want to know what is the concentration of each ion left in solution at the point where the second ion begins to precipitate. Yeah, let that digest for a second, because that's a brainful. So we already determined what's going to precipitate first. That was the silver chloride. So we're not talking about that point. If we move past that, the second ion that precipitates is the lead. So this is the point where the second ion begins to precipitate, where it begins to precipitate. So how much lead is going to be in the solution when it begins to precipitate? Not after it's precipitated, right when it starts. We could. Yeah, we could. Yes. But when they're this far apart, doesn't matter. If I subtract 1 times 10 to the negative 9 from 10 to the negative 2.
Isn't the same as the one you got?
Yeah, I mean, you're right. Like that concentration does disappear, but it's such a tiny amount that we can get ignore it, just like other small x situations. Because if I subtract this from this, is what you're talking about, right? Maybe? No? Okay. 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 All right. I was misunderstanding that. Yeah, so basically we kind of ignore the first one because we're already past that. And actually, we would actually think we would have to add more on top of that to get to this point. But because 0.0177 molar chloride is where the lead begins to precipitate. None of it's precipitated yet. It's where it starts, not after some has precipitated. So at that concentration, if we want to know the concentration of each ion left in solution, the lead is still going to be whatever it started at, 0.085 molar. The silver I didn't even think about sodium. Sodium's one of the ions in solution. Although, we'll come back to that. So for silver, how do we figure out how much is left in solution? Silver started precipitating a long time ago at this point. Kind of. Almost. 99%. So we basically, we do this same calculation here. But now we know what the chloride concentration is going to be. It's going to be this, because that's when the lead starts to precipitate. But what we want to know is how much silver is left in solution. So I'll put a line there because this is, so I'll take the 1.77 times 10 to the negative 10 equals whatever my silver concentration is going to be times what my chloride concentration is. So 1.77 e to the negative 10 divided by 0.0117. 1.512. Actually, really 1.51, and even that's probably too many sig figs. So this 1.151 times 10 to the negative 8 would be the concentration of the silver that's left in the solution. Because at equilibrium, that's all that can be left in the solution. So we don't have to subtract it from anything. The equation just tells us already this is what could be in the solution, the maximum amount that could be in solution at equilibrium. If we wanted to know how much precipitated, we could subtract this from the amount of silver that we started with, and the rest of that would be precipitate, which, because this is times 10 to the negative 8, that means that, practically speaking, all of it precipitated. Oh, okay, so they didn't ask about the sodium ion. I mean, they did say the concentration of each ion, which could just be lead or silver, or it could be also sodium. What would I think the concentration of the sodium ion is actually pretty easy. How much sodium ion is in solution? Yeah, practically. Plus whatever we needed for the silver, but that's practically nothing. So however much chloride it takes, there's also going to be that much sodium present. Cool. All right, so qual. All the way, there we go. Qualitative analysis. It's all about finding the kind of ions present, and doesn't actually involve any, well, not that much measuring, maybe a little bit. So this is going to be using that selective precipitation. And really, you're given a scheme in the lab manual for figuring this out. To kind of guide you through the steps minimum number of steps that you need to be able to find anything that's in the solution. And while that is like super clean cut on paper, complicated but clean cut, it's like you do this, you get that, you do this, you get that, you do this, you get that, you move down the chart. In practice, it is more complicated. So qualitative analysis, finding the kind of ions, whereas quantitative would be the quantity of substances. So for any sample containing a mixture of metal cations, then you add different precipitating agents and then filter away or decant or pipette away liquid from that. So after each, cation, the precipitates are removed. So in my initial mixture here, I've got cation A, B, and C. I add something to that solution and A precipitates. And then we can decant the liquid from that. This also depends a little bit on, as you'll see, and have seen before, precipitates can have different qualities. Like some of them form big clumps and they just sink to the bottom and they're really easy to get rid of. Other ones, you have to use the centrifuge and you got to spin them for a long time and then you can decant away because otherwise the particles just stay suspended forever. So you can decant the liquid and now you've only got 2 cations left there. Then you add a second precipitating agent. Again, decant away from that, remove the solid until you're left with 1 cation at the end. And in general, you want to be as selective as possible at the beginning. So one of the solubility rules that you learn is that most chlorides are soluble except for a few things. So chloride tests are a good first step because they'll only precipitate lead, lead-2, silver, and mercury. So that's why this chart is not necessarily all of the solubility rules, but it's like a solubility hierarchy, which with more selective precipitation steps happening first. So if I add chloride, almost everything's going to stay soluble that could be in there except for these 3, the lead, mercury, and silver. All right, so lead, mercury, and silver. That's after adding 6 molar HCl. Decant those or get rid of those, and then you've got anything that could be left. And sulfides, while relatively insoluble, there aren't many that we would have. So I think like the ones that we'll have are maybe lead, mercury, copper. But if we look at like this list up here, we've got silver, mercury, lead. When we move down to these remaining cations, lead and mercury could precipitate there again, although the mercury is a different oxidation state. But we could also get copper. I'm trying to think of which other ones. Tin. I don't think tin is one of the ones that we have in our lab.
Any precipitates mercury 2 plus?
Yeah, mercury 2 plus only exists as like Hg plus, like 2 mercuries. So that's why it's mercury 2 plus. Sorry, the mercury 1 plus oxidation state only exists in this form. Yeah, that is a weird one. And then we get hydroxides, and we can precipitate all these things out as hydroxides. Aluminum's one of the ones that I always remember being kind of difficult to do. And then you can add phosphates to get these barium, calcium, and magnesium. And then finally, you get these alkali metal ions, which can't generally be precipitated. And so you can use like a flame test to figure out which of those is in there. So after we get rid of silver, lead, and mercury 2 plus, then we can move on to the sulfides. Sulfide is one that's pH dependent. There's going to be a lot of these, or at least a few of these that are pH dependent. The sulfides, hydrogen sulfide is weak acid, and it also smells really bad. I did use sulfides when I worked at the USDA, and we kept a bottle of bleach around because bleach will neutralize the smell. The problem with keeping around a bottle of bleach in a teaching lab is that we will also be working with ammonia. If you mix bleach and ammonia, you get chloramine gas. So I don't know, maybe I'll have Jonathan or Omar be in charge of a chlorine bottle because I really hate the smell of hydrogen sulfide. Yeah, it's not good. Anyways, it is a weak acid, so it's pH dependent. If you are at low pHs, it's going to be mostly protonated and therefore not available to make or to precipitate with other ions, cations. So you have to be at a higher pH. And a big part of this also, I guess we don't have it for the chlorides do have somewhat distinct appearances. But as you can see here, these solids also have distinct appearances. And that is another thing that you can use, not just based on the fact that something precipitated, but also it precipitated, and I've seen this before, because you're going to do all of these experiments and hopefully take observations, take pictures, write things down. Because obviously if you get lead sulfide, that looks very different than the other things. And that's like an immediate telltale that that's lead and not cadmium or antimony. Oh, right. This is at low. So this is one of the ones that you can control, because if you have a low concentration of the sulfide, then you can precipitate the stuff that's less soluble. At low concentrations, it'll precipitate first. And then you can add base, increase the concentration of available sulfide, and precipitate other compounds that wouldn't have precipitated at lower concentrations. There's kind of a double effect. While adding base, though, you can precipitate some things as hydroxides, like chromium, iron, and aluminum. And then after removing all of those, the only things that should be left are the insoluble phosphates. So you add ammonium phosphate, and then get magnesium 2+, calcium 2+, barium 2+. And then remove those solids. And then the only things that can be left are sodium, lithium, and ammonium, which can't be precipitated. It says sodium and potassium can be identified with flame tests, but lithium also.
Yeah, but what color was lithium?
Lithium's like more the magenta. It's a really bright red. That's like my favorite flame test. Potassium is hard to see because potassium is so faint. Like here, this is a really, really good picture of it. In practice, though, it can be hard to see. But if you do see it, yeah, we'll talk about that. I guess we got time. Yeah. Most of the yellow flame that you see on anything that gets hot enough is sodium. And sodium actually produces light at a very, very specific wavelength. That yellow is like one wavelength of light. Actually, they used to use it, this is so random and off topic. They used to use sodium lamps instead of a green screen, because the sodium lamp was such a specific frequency that it was easy to remove. I think that's what it was. It's easy to remove, or they knew which things to keep in. And so like the first, like Mary Poppins was done using a sodium light instead of a green screen or blue screen. Oh, right. And you can use it's called cobalt glass. It's deep blue glass, but it filters out all of that sodium light and lets you see things like the potassium. I guess we don't really have enough. The one thing that I will say about all of the qualitative analysis labs is that there will be extra reagents. And so even when we are doing the unknowns, you can reperform tests with known solutions. So you can mix up your own solution of aluminum or of potassium and other things, and then run tests on those to see if it looks like your sample, to see if it looks like what you think you have. And that's a big part of this, is just knowing, what does this look like? Because until you've seen it, you don't know. Got to train your mental model. Well, I guess there's another part of this what we're going to use, and it's these complex ions, which have ligands. So it's these ions that attach themselves to a metal cation. And especially as it pertains to qualitative analysis, one of the main ones of these is how they can affect solubility. So solubility of an ionic compound containing a metal cation forms complex ions in the presence of Lewis bases. So metal cations are Lewis bases because they are they receive electron pair acceptors. Their solubility can be increased based on the anions present. And I want to really just talk about amphoteric metal hydroxides, because aluminum is one of these. And aluminum does weird stuff because it is not soluble at low pH. Or sorry, it's soluble at high and low pH, I had it backwards, but not at neutral pH. So this is one of the ones that's very pH dependent. And part of what makes it such a difficult test to do. Adding too much acid, or if you've gotten down the line in a few experiments and you've added acid, you've added base, you've added different things to your solution, when you try to do an aluminum test, you need to know what the pH of your solution is and then adjust it accordingly. But if you've added a lot of ammonia, then it might be buffered really well. You might need to add a lot of acid in order to get it back down. Okay, here's the amphoteric hydroxide. So at neutral, it's insoluble, but at low pH, it adds a bunch of waters. At high pH, it adds waters and hydroxides. And it's not the only one that can do this. Also, that's aluminum. Chromium, zinc, lead, and tin all have other complex ions that they can form. And honestly, I think that's all of this chapter that we're going to cover. Maybe you do the 1K off on Wednesday.